So we're going to talk about the basics of magnetism, so how magnets work and what makes them work. First, just a little bit of history about magnets. Magnets come from these stones called lodestones, and they were found in an area called Magnesia, hence magnet, magnesia, magnet. Um, and what they discovered was that these stones, if suspended, would always point in one direction. And so now they could actually use these stones for navigation, whether or not they could see the stars. They could now know which direction to go. So if they're trying to go north, they would go in the direction that this stone was pointing. If they wanted to go east, west, or south, then they would orient themselves using that northern component and then go in that direction. So this was a huge innovation. Magnets and lodestones are made out of magnetite, which is a mineral, and it's the magnetite that is what creates the magnetism. Magnetite is an iron oxide, so the iron in the magnetite, the different forms of iron within it, are what create that magnetic property. Not all iron components are actually magnetic. It's the specific mixture of two kinds of iron that create the magnetic properties that we know. So there are three types of substances. There's magnetic, where magnetic substances can attract non-magnetic substances. So these are what you're thinking about. You stick a magnet on the refrigerator, it is magnetic. Ferromagnetic means it can become magnetic. So if you've ever put something together, you know that if you use a screwdriver long enough, you can actually feel that the screwdriver becomes magnetic. And that's because it's made out of iron. And so ferromagnetic materials are not naturally magnetic, but when they're in the presence of a magnetic field, can become magnetic. Non-magnetic materials, and ferromagnetic is iron, nickel, and cobalt. These are the only three elements that can become magnetic. So not all metals are magnetic, but these three metals can become magnetic. Non-magnetic materials are things that no matter how strong a magnet is, that material will never become magnetic in the presence of the field. So this would be copper. You can never get a magnet to stick to something that's copper, aluminum. Then, of course, all your non-metals, paper, wood, plastic, things like that. So non-magnetic will never become magnetic. Ferromagnetic is not naturally magnetic, but can become magnetic, and of course, magnetic's always magnetic.
So the fundamentals of magnetism is all based on this top thing where it says that magnetism is created by moving charge. So whenever we were talking about static electricity or current electricity, we were talking about moving charge as well in the form of the electrons. In static electricity, we're moving electrons from one object to another, creating positive charge and negative charge. In current electricity, we were moving charges, moving electrons through a wire, thereby creating current. So the electrons around an atom are constantly moving. So that is around an atom itself, and then again, like we were saying, moving those electrons around. Because electrons are moving charges, each electron inside of the magnet, or inside of any material, can act as a tiny magnet. This tiny magnet can then add on to another electron, another electron, another electron, and that's what creates the magnetic properties of a particular magnet. So the more the electrons are aligned, the more the electrons are moving in the same direction, then the more magnetism it has in that direction.
Magnetic domains. This is what actually creates the magnetic properties in a magnet. A magnetic domain, by definition, is a cluster of atoms where the electrons spin in the same direction. So electrons are going around the nucleus of an atom, and if the electrons are all going in the same direction, that grouping is called a domain, a magnetic domain. And so down here, this is a non-magnetic material. This section of the magnet are all of the atoms that are all lined up in this direction. This little section is where all the electrons are lined or are spinning in the same direction going this way, and so on and so on. These are microscopic, you cannot see them. And the difference between regular iron and magnetic iron is these domains. Non-magnetic iron still has magnetic domains. The difference is that the domains are going in different directions. For magnetic iron, all the domains are going in the same direction. So this is non-magnetic, this is magnetic, because you can see that all of those domains are lined up together. This is kind of like a vector issue. If all the arrows are going in the same direction, they add up. And so you have a strong field because they're all going the same direction. For non-magnetic, they're all going in opposite directions, so they can subtract from each other. You have one going up, one going down, so those cancel. These are going opposite directions, they cancel. These are going opposite directions, they cancel. That's why it is non-magnetic. But they do have these little magnetic domains within them. So in terms of strength of a magnet, if all of the domains are going every which direction, they're all canceling out from each other, it's unmagnetized. So not very strong. If they're generally going in the same direction, you have a weak magnet. So these are the ones that are like the advertising magnets that you can put on your refrigerator for different companies. They can't really hold much, maybe, if you're lucky, one sheet of paper, but that's really it. And then you've got those really strong magnets, the ones that just like snap onto the refrigerator. And those are your ones where all of those domains are all lined up perfectly. So very strong alignment of domains. So magnets have two poles, and we call these north and south. And it's not that it's a north pole and a south pole. It's that the north end, the one that's labeled as an N, or is normally red, seeks the north pole of the Earth. So when we're talking about those lodestones, if you suspend a magnet, the north-seeking end of the magnet will always point towards the North Pole. The south-seeking end will always point towards the South Pole. And just like with electrostatics, opposites attract. So north and south will attract, and like poles will repel. So north and north will repel, south and south will repel. So magnets, because of these aligning of domains, the poles are not like these electrons are pointing this way and these electrons are pointing that way. It's that the alignment creates this loop of magnetism. And so since these domains are lined up in the same direction as these domains, if you were to cut this in half, then these electrons are still spinning the same way. The domains are still lined up in the same direction. So what happens is each piece now has a north and south pole. North-south, north-south. And so you cannot separate the poles of a magnet. And it's because those electrons are always going the same direction. So you can keep breaking this, and each piece will always have a north pole and a south pole. Same here, if you break it long ways, so break it, hot dog style, then you'll still have the north and south-seeking poles. Compasses work because they are little mini magnets. So in a compass, any compass, the needle of the magnet, or the needle of the compass, is actually a tiny bar magnet. So you have the north-seeking end and the south-seeking end. When a compass is placed in the Earth's magnetic field, then the north end of the compass will point north. So it will seek the North Pole. The south-seeking end will seek the South Pole. And that's how a compass will be able to tell you what direction you're going. Now, if you were to put a magnet, so any other magnet near this compass, the compass will align with the strongest magnetic field that it feels. And so if it's the Earth, then it'll align with the Earth. If there is another magnet placed next to it, relatively, that one is stronger, so it will align with the other magnet. So how can you make a magnet? Well, one thing is by contact, right? So if you touch a magnet to a nail, the nail will become magnetic. This is how magnetic screwdrivers work. The nails and screws, or the screws are just iron containing. The screwdriver is magnetic, and so they stick together. Another way is by induction. So way back in the day when we talked about induction, induction is without touching. And so if you bring a magnet near a ferromagnetic material, it can induce a slight magnetism. And then, of course, there's by electricity, and these are what we call electromagnets. So you bring a current through a wire, and that current naturally has a magnetic field associated with it. And so you can create these electromagnets. And so how do you think lodestones were magnetized? Well, they were magnetized by the magnetic field of the Earth. So the Earth has a magnetic field, and whenever these lodestones were solidifying on the surface, their domains lined up with the Earth's magnetic field. That's how they became magnetized. So how can you demagnetize? Well, the first one is heat, right? You heat something up, the atoms start moving more, the electrons start moving more, and they can get knocked out of alignment. If something is moving fast enough, it's going to start going crazy. The other one is by contact. So if you put two magnets together and you put it like North Pole against North Pole, eventually one is going to be slightly stronger and will cause the other one to demagnetize. So just in contact with another magnet can demagnetize. And of course, hammering. So if you were to drop it, if you were to hit it really hard, again, it can cause those electrons to move, to change, and it can cause them to become out of alignment. So heat, contact, and hammering.
So now that we've talked about the basics behind magnetism, why don't we talk about factors that can affect magnetic force? So the first one is, of course, the charge. And so the charge is, of course, how many electrons there are in that certain amount of charge. Since moving charge means that there's a magnetic field, then that means the more charge there might be, then the stronger the magnetic force will be, because it's all about moving charge. The second one is speed and velocity. Well, that's how fast that charge is moving. So the faster the charge is moving, then the more the velocity is, then the stronger the force is going to be. The last one is magnetic field. And so if this amount of charge is in a magnetic field, which is where the force is between this charge and the magnetic field, then the stronger that field is going to be, then the stronger the force. So taking those three factors, charge, velocity, and magnetic field, where charge is going to be your Q, velocity is V, and then magnetic field is that capital B, we have our equation F equals QVB. Notice since everything is multiplied together, these are all direct relationships. So the more Q you have, the more force. The more V you have, the more force. And the more B you have, the more force. So we've gone through these three a lot extensively. So force is in newtons, charge is in coulombs, speed of velocity is in meters per second. This is our new one, which is capital B. Capital B is the magnetic field strength, and those are measured in Teslas, because Tesla was the person who came up with the idea of magnetic fields when he was creating alternating current. So why don't we do an example using this new equation now. So we're going to go through the givens, equations, substitute, and all that solving stuff like we usually do. So the first one is this 10 Tesla. That is going to be our B value. So B equals 10 Tesla. This is our coulombs. So that's going to be our Q value. 2.5 times 10 to the negative fifth. So E, negative 5 coulombs. Make sure it's in the calculator correctly.
And then this is in meters per second. So that's going to be our V. So V is 50,000 meters per second. So there's all our givens. We are looking for the force. So new equation, F equals QVB. We're going to plug everything in on this side. F equals 2.5 E negative 5 times V, which is 50,000, times 10. And if we multiply all those together, this times this times this, we get 12.5. Since it's force, F is force, force is measured in newtons. So final answer, 12.5 newtons. So now here we go, example 2. For example 2, all right, here we go, example 2. So for example 2, we have a proton. And notice it is bolded and underlined, which means this is important. What do we know about a proton? We know that its charge is equal but opposite to an electron. The charge of an electron is negative 1.6 times 10 to the negative 19. So a proton will be positive 1.6 times 10 E negative 19 coulombs. This 90,000 is going to be our meters per second. So that's our V. V equals 90,000 meters per second. And now we're given the force. F equals 30 newtons. So what we're looking for is the strength of the magnetic field. That is our capital B. So same equation, but now we're solving for something on the other side. F equals QVB. F is 30. Q is 1.6 E negative 19. V is 90,000. And looking for B. First thing I would do is combine these two numbers. We multiply those together in the calculator. We have 30 still on this side. This side we now have 1.44 E negative 14, and that is times B. And then to get B by itself, we're going to divide both sides by this 1.44. There we go. So these cancel out. On this side, we're left with B. So I'm going to just put that over here. And if we divide these two numbers, we get a really big number. 2.08 E 15, or 2.08 times 10 to the 15th. Capital B is measured in Teslas. And that's our final answer.